Welcome back to the most exciting lesson of the year. My fingers are crossed behind my back because I'm lying a little bit. Actually, I don't mind this one. It's pretty straightforward. Lots of writing for me, but concepts aren't that difficult. Okay, so this lesson kind of ties into what we were doing yesterday. And we looked at some polyprotic acids and bases, but I didn't really use that terminology with you. I just did some examples of them as we were looking at those tricky questions where you had to show the successive reactions. So anyway, we're going to solidify those concepts today so that by the end of today's lesson, you've got this all dialed in and you're good to go. So polyprotic means many protons. These are acids that have at least 2 protons to donate. So you'll see H2X or H3X. And then polyprotic bases or polybasic species are going to be at least X2 minus or X3 minus. So they can gain 2 or 3 protons. So you've got this definition here. Any base capable of accepting more than 1 proton, 2 minus or 3 minus. So a good example is sodium carbonate, which donates into 2Na plus. I should say dissociates into 2Na plus and a CO3 2 minus. So that 2 minus is the key to telling you that this thing can accept 2 H pluses. And they tend to gain them sequentially, not perfectly, but the 2 minus will gain protons from water. So that means water is acting as our weak acid, and this is our weak base. And you know that any weak acid and weak base will react less than 50% in equilibrium to create these products. Now, this product is also a weak base, so it can react again with water. Here's the part you have to remember. If this is a weak base with a 2 minus, this is an even weaker base with a 1 minus. So I could write here weaker base. So if it's an even weaker base reacting in water and the first one only accepts less than 50%, as a rule, the second base only accepts less than 5% of the protons from water. So the rule is less than 50, less than 5, and if there's a third one, if it was X3 minus, less than 1%. So you're getting less and less hydroxide produced, which means that they have less and less impact on the pH as you accept the second and third proton. Okay, what if we reacted it with a strong acid? Exact same diprotic base, meaning diprotic, it can accept 2 protons. So first proton goes. How many of them go if this is strong? 100% quantitative, making that weak base. So weak base 1, weaker base 2. With a strong acid, how many of these will go? It's still 100%. And we get that. Okay, now because they were both quantitative or complete, we can add them up. Those top ones, we couldn't add them up because they never reach all. We don't know how much of this is produced and we don't know how much of this reacts. We just know a very small percentage of it. On these, it's 100%. So because it's 100%, we can add them up. And we've done this before when we did redox chemistry, I think. Was that the unit? Ooh, no, it was Sudoku's thermochem. If you have something on the product side and the reactant side, they cancel out. So when we add this up, it's CO3 2 minus reacts with 2H3O plus to give us H2CO3 and 2 waters. We've removed the HCO3 minus because it was 100% produced and 100% used up. So this would be our net equation for that acid-base reaction. So water versus a strong acid gives you a very different outcome. All right, let's take a look at diprotic, triprotic acids. So polyprotic acid is any acid capable of donating more than 1 proton, H2X, H3X. when I took a course like this in university, the prof made up fictional acids like H5X and would ask us what that would do. So this is an H2X, H2SO4. It's polyprotic or diprotic. And here's an example of a triprotic. This thing has 3 COOH groups. And remember that H is acidic proton on the carboxylic acid group. H2SO4 is interesting. It is an exception to the rule. It is the only strong acid that's polyprotic. All other polyprotic acids are weak. So they follow the rule. Less than 50%, less than 5%, less than 1% when you are reacting them with water as your weak base. So I'm going to show you the exception to the rule because this is a strong acid, and a strong acid in water is greater than 99%. So it goes to completion. This weak acid can react a second time with water and donate a proton, but it's a weak acid in water, so it's less than 50%. So can we add these up? Nope, we cannot, because this second one is stuck in equilibrium. It's going back and forth, back and forth. So we never know the exact final amount of sulfate ions and hydronium ions. So that's how you would show sulfuric acid as a diprotic strong acid. So that's an unusual one. This next example is more typical because this is a weak triprotic. All the polyprotics are weak except H2SO4. So show how this thing will react with water and then how it would react with a strong base. So a weak acid in water would give us less than 50%. Now this is also a weak acid because it still has 2 protons to donate. Most of my time is spent writing this thing out. C3H5O, COOH, 2. I think I did this one as a challenge question last class. Okay, so it will donate one of those protons, C3H5O, COOH. Now there's only one acidic proton left, and we have 2 of those COO minuses, and we get our hydronium. Now, I put a single-headed arrow, but that's equilibrium. If the first proton is less than 50, the second one is less than 5. And this is also a weak acid. It has 1 proton left, C3H5O, COOH. There's that acidic proton. COO minus 2 plus water donates that last proton to make C3H5O COO minus. There's now 3 of those that have lost their protons and a hydronium. And if that's less than 5, this is less than 1%. Okay, so there's our pattern. Less than 50, less than 5, less than 1. Okay, how would this change if we used a strong base? If we used a strong base, you would get a complete reaction. Now the next ones are going to look the same. Let's see how fast I can write this out. They're going to look just like the top ones, except every one of these is quantitative because of that strong base. And H2O, and then the last one, C3H5O, COOH, COO minus 2, and a strong base gives us greater than 99%. C3H5O, COO minus 3, and water. Okay. Why did I take the time to do this? Because I wanted you to be able to see what this looks like when you get a net equation, which we can do because these are all complete. They're all greater than 99%. Can you believe it, Cassie? How fascinating is this? All right, so we got to be able to cancel out what's reacted and what's produced. It's the same. So this one is the same. And let's go with another color. This one, oh, I didn't switch it up after all that. You think I had this thing figured out by now? Okay, that one's the same. So we end up with C3H5O COOH 3 plus 1, 2, 3 hydroxides gives us C3H5O COO minus 3 plus 3 waters. Phew, that's a lot of writing. And there's our net equation. So that's triprotic. 3 protons donated to 3 hydroxides to make 3 waters. And again, that only works if you have a strong base. If you have a weak base, then it just gets weaker and weaker. Our acid gets weaker and weaker. Okay, what are some triprotics? Here's the exception to the rule, or polyprotics. Okay, now we're down into the weak acids. This one is polyprotic, COOH on both ends. There's a triprotic. Here's a triprotic. Okay, what else? Diprotic. There's a bunch of them in here. Mono, mono, mono. That one's diprotic. 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 You get the idea. This thing's full of them. And then for bases, 3 minus, 2 minus, 2 minus, 2 minus, 2 minus. Those are all polybasic. 3 minus, 2 minus. So they can accept 2 or 3 protons. Okay, that's first half. Done. Whew. Not as long as yesterday's lesson, but still decent. Tomorrow's like 15 minutes and we're done. Yay. Okay, so take a look at this pH curve. These are a little different than you saw yesterday. Yesterday you saw pH curves that looked like that or like that. So starting with a base and adding an acid, or starting with an acid and adding a base. So this curve has, and they had one equivalence point, and it could be at 7, above 7, or below 7. So now this titration has 2 equivalence points. Why does it have 2? Because it has a diprotic base. So if I go back to this slide, here is our CO3 2-. When this reaction is done 100%, that's your first equivalence point. Then the second strongest base starts to react. And when it's done, you get the second equivalence point. So the idea is when you're looking at a pH curve, you should be able to explain what's going on. So I should have wrote that up here. This is CO3 2- reacting with our strong acid. And at this point, it's done. And we start on reaction number 2, which is the HCO3- reacting with the strong acid. And at this point, reaction is done. And after that, we're just adding a strong acid to water. So that's something you should be able to do. Look at a pH curve, given the reactants, show the Bronsted-Lowry reaction that's happening in each region. I know you're not writing a diploma, but on the diploma exam, they would number these as regions 1, 2, and 3. And they would say which reaction is occurring in region number 2. Or they might say which region shows this or that. So anyway, that's how they would test you on that. Okay, so that's a diprotic base with 2 equivalence points. Okay, let's take a look at this one. This is H3PO4, a triprotic acid with a strong base. Okay, so we're starting with the acid down here and we're adding the base. If you have to predict the equivalence point, you pick the steepest part of the inflection or the curve right in the middle. That's equivalence point 1. So at that point, reaction 1 is done. What is reaction 1? H3PO4 plus OH minus makes H2PO4 minus and water. Okay, so what happens in, we'll call that region 1. Region 2, what happens in region 2? Our next reaction, which is this diprotic acid. H2PO4 minus reacts with hydroxide to make HPO4 2 minus and water. Now that finishes right there. That's about the middle of the steepest slope of the curve. So we call that equilibrium point 2. And then the third reaction would be HPO4 2 minus reacting with hydroxide. Now, normally you would expect that because this is a strong base, this one would go to completion as well. But this acid is so weak, there's no third equivalence point, which means it never reaches completion. So this one is actually stuck in equilibrium. Okay, I don't know the percentage, and you don't need to know it either. It's just not complete or not quantitative. If it was, we'd have our third equivalence point. So there are some exceptions to that rule. Okay. You could pick an indicator for either one of those equivalence points. So the first one is at 4 and the second one is close to 9. So knowing that, you could go to your curve and this would be a great indicator, 3.8 to 5.4, 3.2 to 4.4. Both of those change color with that 4 in the middle somewhere. And then the second one was 9. So that would be a good indicator, probably the best indicator, phenolphthalein. 9 is almost right in the middle of its color change. So equivalence point 1, if you wanted to stop there, stop your titration. Or if you were going to stop it after equivalence point 2, you would use that indicator. Okay. Now, this next part, what we're going to do is I'm going to ask you guys, what would the curve look like for this titration? It says to show 5-step method, but we're not. We're just going to do a pH curve instead. So we have K2SO3, 2K pluses, SO3 2 minus, a strong acid, H3O plus, Cl minus, orange 4, which I believe is HOR and OR minus. It'll have both of those. To change to orange 4 in your notes, so you had something different before. Okay, so we're starting with a base. So we're going to be starting up here, and it's a weak base. So let's go with around 12. We're just guessing. It is diprotic, 2 minus. So if you sketch it out, you're going to have 1 equivalence point, 2 equivalence points. And we don't know those exact pHs, and you don't need to. We're just going to say that we know we're going to finish with a pH of less than 7 for sure on our second one. Okay, so sketch it out. And then we have this orange 4. So where would the orange 4 change color on this pH curve? If we don't know these pH values, how could we figure that out? Would orange 4 change color on the first equivalence point or the second one? Okay, well, let's go look this thing up. SO3 2 minus. How do I get there? Darn it. This mode. Whoops, let's try that again. Okay, hopefully I don't lose this slide. Get out of there. Darn it. I was jumping back. Oh, I know what I need to do. I need to go like this. That does it for me. Okay. I gotta go see what I had lost my train of thought. We were gonna go and look up. Oh dear. Where are you? Where are you? Where are you? Get rid of that one. Where are they? Where are they gone to? Swipe up to Chrome. Okay, I'm going to pause this. I'll come back in a sec. Okay, I'm back. I have my glasses on. I had to go do some searching. Okay, so we want to look up whether or not orange 4 will react for region 1 or 2 or where it's going to happen. So I'm going to scroll up to my 2 tables of relative strength. So I found orange 4 here in the acid-base indicator. It's 1 times 10 to the minus 2. So we're going to go stick that in our table of relative strengths. It belongs right here. And HSO3 minus is just above it. So here's our strong acid, and we're titrating with SO3 2 minus. So there's our first reaction. So that one's done. Then we move up the table, and the strong acid will go after our next strongest base. So which of these two, the OR minus or the HSO3 minus? And correct answer is it goes with the strongest base, which is OR minus is stronger than HSO3 because it's below it on the table of relative strengths. So in this reaction, the indicator would go second, and then our HSO3 minus would go third. So if we had to draw the indicator on here, we'd put it happening after region number 1, but before region number 2. Because this one, so this reaction is done. This is our first one, which is SO3 2 minus and H3O plus done. And then the H3O plus goes after the indicator. So immediately after that reaction's done, the indicator changes color. And then in this region, the HSO3 minus would go next. And here it's done. And then all we're doing after this is adding H3O plus to water. So those are a little tricky, a little hard to do. Will phenolphthalein show when the second endpoint has been reached? So phenolphthalein changes from like 8 to 10 for a pH. Would it show the second one? No way. It's going to be up in this region somewhere. Phenolphthalein's a dud. If you want to show the second one, you need an indicator that is above the sulfate ion. So let's just go look at that again. So our sulfate, HSO3 minus, is right here. You would need an indicator that is sitting to the -1 just before we get there. And there's only 2 indicators that are that weak as a base, and it's these 2. To the -1, to the -1. Methyl violet and cresol red, MV minus and HCr minus, they would react after the HSO3 minus as really, really weak base indicators. Okay, the last example. This is a review. I'm going to do this one as a review. No, I'm not. We did this already. I'm not going to do this one. This is that tricky guy. C3H5OCOO. It's missing its -3. If this thing's titrated with a strong acid, you're going to have 3 steps, right? And methyl orange. So you would have to figure out where methyl orange goes in those 3 steps. And I don't think I need to do that. I've done enough polyprotics to put you to sleep. How would these reactions differ if water was added? So if we change that out and did water instead, we would get less than 50% on the first, and you would get no equivalence point. You only get equivalence points or endpoints when the reactions are complete. And that's why in a titration, you always have to use a strong acid or a strong base to get 100%, because only at 100% do you get an endpoint. or equivalence point. So water is out. Don't use water in your titrations. You'll never get an equivalence point. You can react all day long, keep adding, and it never reaches the end point. Okay, so I'm not going to do this one because you have an example in your notes of that triprotic in order. Just remember that, well, I don't have to go through it. We're done. Okay, so if you would like to practice these, there are some questions in your textbook. I will put the answers. It says Google Classroom. I'll check if they're there, and if they're not, I'll put them in this lesson for you. Okay, lots of content again today, but that's it. Tomorrow, short and sweet. And then we're done. Okay, take care, everybody, and we'll see you tomorrow.